Yeah, very good morning. Am I audible?
Yes, sir.
Okay. And the class, or sorry, this uh, slides are is visible to you?
Yes, sir.
Hmm. Okay. So, yes, so let's first get the feedback of midterm exam. So I think exam was easy, medium, or tough. Can someone comment?
So the integral parts were a bit tough.
Ah, okay.
Overall, it was medium.
Ah, okay. Mhm. Okay. Fine. So, do you have any question regarding midterm examination?
So will we be awarded step marks or
No, see, this we have taken your rough notes so that means the debate can be there later on. We suppose uh, if very silly mistake is there, means like some evaluation, something like that, we may try to consider it. Okay, you see, that means like anyway the marks will be awarded based on the final answers, but still if there is any discrepancy we will try to attack it. Okay.
okay, sir.
Yeah. Hmm. Okay, so if you gone through the syllabus, we have covered almost half of the syllabus. Now we have covered, I think, differential calculus, and I see. Okay, so now we are going to move towards the vector calculus. Okay, so we are not going to repeat the things which you have learned already regarding the vectors, vector magnitude, distance. Okay, those stuffs. Okay, we are not going with that. So what we are going to do is we try to uh, see that how to integrate, okay, a real valued function along a curve, okay, along a curve, along a path, you can say, see that we are going to denote. Okay, later on we will also try to see how to integrate vector fields. So you will soon know what do you mean by vector fields, what they will represent in real phenomena. Okay, and based on their based on their classifications, means like so sometime the vector field represents the force, or it may represents the velocity field of a fluid, and so on. Okay, so that we will try to see how the physicists, or you can say in the real world, how the this line integral or surface integrals, okay, or means will have an attached name, and how means like in the means specifically like work done, or what we can say is the fluid flow across the curve or along the curve, and so on. Okay, so we try to address them as well. Okay, right. So uh, let's discuss this line integral. Okay, so this already explained that this integration, such type of integrations are used to describe flow design. You can say underwater transmission cables. It may also explain the flow of heat in stars. It may also describe the how to put satellites in orbit and so on. Okay, so let's first concern about the line integrals. Okay, so I may give a very realistic example, means like in the words that work done by a force field. So this force field can be a type of gravitational force, or it may be an electromagnetic force of some kind. Okay, and you are moving means with some force, you are moving in some or you are moving along the curve. Okay, or along the path. How much work done, total work done is done. So see, again, it's going to be giving you a scalar quantity. Okay, is a number. Okay, total. Okay, so integral ultimately value will be a number. Okay, that we will be concerned about. Okay, so let's start with this line integrals. So let this f of x comma y comma z be a real valued function with domain D. So it's see, once I write this statement, it is very clear that f is from D to R, and this D is a subset of some R. And I hope now, being in a function of several variables, you know what do we mean by R3 is a space XYZ space, you can say. Okay, so this domain can be a tetrahedron, or it could be a cube, and so on. Okay, so let f is defined on this particular domain, and it's a real valued function. We are only concerned about it. Later on, it can be extended to complex valued as well. So we are not concerned right now for that. So let's restrict with the real value. Okay, so and let a C be a curve. Okay, let C be, so you have a domain D over which the f is defined, and C is a curve that lies inside D. Okay, so you have the starting point and ending point. Okay, so I have given this direction along which it is moving, like it may move in this direction, or it may move in the reverse direction. I don't right now I can't see. So specifically, let's mention this the direction of this C, or orientation of C is, this is starting point and this is ending point. Okay, and when you then you will parameterize this curve. Okay, so parameterization of the curve. So at time t equals to a, its starting point is, means like you say, what I say is r of a will be this starting point. This is r of a, and this is r of b is their ending point. So t equals to b. And along this in the space, you have parameterization x of t, y of t, z of t. So it could be it's a function of t specifically. Okay, and I mean, see, it's a t is a dummy variable. Again, I'm telling you, it may change, depends on the situation again. Okay, so right now means more specifically, the applications are oriented towards the time domain. So that's why it's a more general. It is given with the function of t. Okay, otherwise it may be denote the arc length parameter, then you have s. Okay, that's a standard notation, and so on. Okay, right. So so you have parameterization. So it may, you may have this as a helix or something. Okay, so that we will see. Okay, some of the curve. Okay, maybe soon. Okay, and we'll see how what kind of parameterization. So in the polar, or sorry, in the this you can say in the if you have this C is a part of a circle. Okay, C is a part of a circle, so you have x, means like that x square plus y square equals to 1. Z component is not there, so if you remove this component, you are talking about it on the plane. Okay, so That I mean, see, slowly we will try to understand. So if you have a part of circle, so you can define x of t equals to cos t and y of t equals to sin t and z of t equals to 0. That will give you the parameterization of that part of the circle. That, and if you have the first quarter of the circle, means that t lies between 0 to pi by 2. Okay, so I hope you can recall that fact. Okay. Now, what we wish to do is we wish to integrate. So let's talk about the three-dimensional one. Okay, that can be also, that is a that you can understand as a generalization of this two dimension. So we wish to integrate f along this given curve C. Okay. Now, for so again, we are going to use the Riemann's approach, since you have the end point and initial point and end point. Okay, means it's a bounded. Okay, and we are also understanding that this curve is a smooth. What do we understand by smooth curve? Okay, so let me mention that first. So if I say a curve is smooth, smoothness of the curve, what does it mean? Is you have dr by dt, which represents, so if you, which represents the velocity vector. Okay, is continuous. Okay, is continuous on closed interval AB, in starting point A to B. Okay, and yes, of course, how do you understand this? A vector is continuous whenever each component is continuous. So suppose if I want to say this vector R is continuous, each component x of t, y of t, z of t, all should be continuous functions. Okay, or in other words, in every direction you have a continuity. Okay, so there are three directions. So in every direction you have a continuous curve. Okay, so a smoothness means the derivative is continuous and this velocity vector is non-zero. Okay, and velocity vector is non-zero vector, never be zero. Okay, that will represent the smoothness of the curve. Okay, so, and again, this is also known as the tangent, right, at any point. Okay, right. So now, so for doing the above, what we can do is, if, as mentioned, we are going to approach with the Riemann's. Okay, so you are going to subdivide this curve. Okay, you are going to subdivide this curve in the partitions. Okay, by a line element. Okay, and if you subdivide and if you total it up, it is going to be a arc length. So this is going to be denoted by ds. S is the arc length parameter, then this is going to be ds. Now, over which the function is defined, and now you can choose a tag point. Okay, so to choose a tag point xk comma yk comma zk, then f of xk comma yk comma zk. So that the story will repeat the same. Okay, so I hope I have the final one here as well. Yes. So by choosing a point xk comma yk comma zk in each sub arc, we form the Riemann sum. That is easy to follow because we have gone through many many problems, such problems, double integral, triple integrals, and so on. Okay, now, so again, if you have this limit, okay, limit of Sn, means if you increase the number of partitions exist, then it will be says as integral along C f of x comma y comma z. You have, this is going to be ds, right? Yes. So in the limiting case, this is now. See, now I'm here also. I want to mention that sometime you will have the notation in the integral like this circle as well. Sometime it means that you have a C is a closed curve, okay, and it is oriented in the positive direction. Okay, so this notation means integral along a positive curve. If you remove this, we don't have any, means like we don't know first hand that C is a closed curve or not. We have to see the graph of the curve and see whether end point and initial point meets or not. Okay, are they the same or not? Okay? So this is called the line integral. Okay, so
Sir.
this is what. Yes.
Means f of x comma means this function x y z. All the three are independent, so we cannot plot it in 3 dimension. No? Means.
So three independent. Yes, it's a you can say it's a 4-dimensional problem if you include the time domain. Yeah, you can't plot. Yes.
Sir, so in how
Plot means plot means say you can. It means you have to take some tools. Means like in MATLAB or somewhere. Okay. Means you have to specify the points t equals to parameterization and then you can certainly plot.
Sir, but we have to make it equal to some dependent variable, and then we have to plot in 4 dimensional, no?
So see how you have plotted f of x comma y. You have put it down z equals to f of x comma y. So
yes, sir.
similarly, if you have this is u equals to f of x comma y comma z. So you have 4 dimensions.
Yes, sir. So how in this graph, in the slide, it is shown f. Means
So
it is
here
3-dimensional curve, and then the f is 4-dimensional.
see, one thing is wait, just I see f of x comma y z equals to c. You can say c is it means if you represent this as this is a level curve. Okay, means u equals to c is a fixed at that level. Okay, now if you you have asked me a very tough question. Okay, it is means you have this is in this here it is going with respect to see if you have this curve. I have this let's take one example. Let's have this. I think I will be able to draw. This is let's say x of t is equals to cos t, y of t equals to sin t, and let's take z of t equals to t, and t is you can take 0 to 1 or something. Okay, now how it will looks like here is so in the xy plane t equals to 0 means in the xy plane it is a circle. Okay, but it is a moving continuous manner, so it will be giving like a spiral, or you can say helix you will get. So from 0 t equals to 0 to t equals to 1. So t equals to 0 to t equals to 1 means z of t equals to, this is the highest point is here is z equals to. Okay, this is a one example I can give you. This is called helix parameter, right? Is that okay?
Yes, sir. Means by parameterizing we can plot the same thing.
Yes, yes, you have to parameterize. Without that, you can't. Okay. Similarly, if you talk about the surfaces, you have to also parameterize that. Okay. Otherwise, it is very difficult to look at. Okay. Yes. So this is one example of, I think, helix. Okay. Right. Now, so as already told, this is called the line integral. Now, ds is the arc length parameter. What is ds is, yes, so if you if r of t is smooth, okay, for a I mean see what is this when you use the parameterization, so at any point it is looks like x of t comma y of t comma z of t. And what is ds? So ds you can divide by dt and multiply by t, and you have the limits t equals to a to t equals to b. Now, if you look at this ds by dt is nothing but the magnitude of velocity vector, right? That arc length, the change of displacement with respect to time is going to be the velocity, right? So it's going to be scalar component, so mod v of t. So that's going to be the final, you can say, a formula which will come here. Okay, so this will be giving you the line integral. Sometime in short, we just also write is L dot I dot. Okay, line integral. So for surface integral, you will see the notation S dot I dot. So that will be later followed. Okay, I already mentioned what do we understand by the smoothness of the curve. Okay, that velocity means that dr by dt should be continuous and it should not be zero. Okay, right. Now let's so what we have to do for evaluating the line integral for real valued functions. So we want to integrate a continuous function over a curve C. We will follow the following step. So first you have to identify a smooth parameterization of C. Okay, and then evaluate the integral as this. Now see, if you replace, so you can also signify this physical interpretation here. If f is 1, so it will give you the length of the curve. Okay, so if you fix f of x, y, z, so you are integrating c ds. So ds is the arc length parameter. It's a very small element. If you sum up all the things, all the ds there, so it will be giving you the length of the curve c. Okay, so if you replace f, or so if you are interested in finding the length of the curve c, you have to simply integrate c over ds. So what is ds is mod of v of t dt. So you have, this is a mod of v of t dt. So you can verify this by looking at this what's it called is by looking at the parameterization of a circle, and you can find out the length of that curve c. Okay, right. Now let's do this problem. So first problem, we wish to integrate f over the line segment from this. Okay. So in the first example, we have f of x comma y comma z is equals to x minus 3y square plus z. And over the line segment from 0, 0, 0 to 1, 1, 1. And C is the line segment joining points. You have 0, 0, 0 to 1, 1, 1. I think it is written 2, right? Yes. So 2 means from origin to this point. And you know, if you have 2 points, you can define the line segment, and it is very easy to get. So I can straightforward write. So C is the curve with x of t is equals to t, y of t equals to t, z of t equals to t, where t lies between 0 less than equals to t less than equals to 1. It is very straightforward. Okay, right. And how it will be looks like in XYZ is you have, this is x, let's say y, and this is z, and this is somewhere point is, let's say this is 1, 1, 1, and you have this origin. So it can be in it's like you have a rope, okay, tied at the origin, and you have just stretch it along a direction. You can say it's like y equals to x something. Okay, is where x of t and y of t and all are equal. X equals to y equals to z. Right now we so this curve is the line segment, So this curve is smooth, there is no problem, because this you can see that the function of, now you can imagine them as a function of single variables, and you can individually decide all of them are continuous. So their derivative also continuous. And you see the derivatives are 1, 1, 1. And you see the derivative, that velocity vector will never be 0. So that's it can be verified that C is smooth. C is smooth. Okay. Now we are interested in finding this line integral. Okay. So now, so therefore, line integral is equals to integration of just again writing f of x comma y comma z ds. This is equals to integration C f of x of t comma y of t comma z of t time you have ds by dt and dt multiplication mod of v of t time dt. So, and we know this is going to be, so t limit is from t equals to 0 to t equals to 1. Now we have to, so you have r of t is equals to ti plus tj plus tk. So velocity vector, you can differentiate, right, dr by dt. How it is defined is you are differentiating in each direction separately with respect to t. So it's going to be I plus j plus k. So this implies magnitude of velocity vector that I think you are comfortable with is going to be square root of 1 square plus 1 square plus 1 square. So that's going to be 3. Okay. Now you have to identify what is f of x of t, y of t, z of t. You have to just simply replace. Okay. Also f of x of t comma y of t comma z of t is equals to x of t minus 3y square plus z, right? X minus 3y square plus z. So x of t minus 3 times y of t whole square plus z of t. So now everything is here t, so t minus 3t square plus t. So that's going to be 2t minus 3t square. So what will apply? So therefore, line integral is equals to integration 0 to 1 2t minus 3t square time mod of v of t was square root of 3 dt. Right now it is easy to integrate. So square root of 3 time you have integration of 2t is t square, 3t square integration is t cube. Upper limit minus lower limit. So lower limit will not contribute anything, t equals to 0. Upper limit will 1 square minus 1 cube. So that's going to be 0. Okay, so line integral will also give you the value 0 when you are integrating f over certain curve. Now, on the other hand, suppose you change the mind. Okay, suppose now this is a one, so you can understand this now. So you are actually starting from the 0 0 and you are arriving with 1 1 1. Okay, now what you can also have is there are various ways to reach this point. So there are ways, means like you may first go to 1 1 0. Okay, and then you will be reaching to this. So there are two. So this is C1 and this is C2. Okay, so see there are multiple paths to, I'm trying. So this is the first example is over. Now I am trying to explain. So if you choose a different path, okay, so means you may understand that you may get the same value or it may be different value. We don't know. Okay, so now, so you have this C1 curve and C2 curve. Both are smooth that you can easily find because C1 is also a line segment joining the point 0, 0, 0 to 1, 1, 0. And this C1 to C, this point, so you have OAB. Okay, and AB is also a line segment, which is also smooth. And you can also write this C1 is a curve. You have this is R1 of T, that is equals to, you have this is Ti plus Tj plus 0k. Okay, and what about C2? C2 is you are just moving towards the parallel to Z axis, right, from 0 to 1. Okay, Z equals to 0 to 1. So what is C2? Is a sum R2 of T, that is equals to Tk. So here also T lies, C is from 0 less than equals to T less than equals to 1, and for this also 0 less than equals to T less than equals to 1. So I have defined both the curves now. Right, Z equals to T will be the curve. Okay, now along C1 you will integrate, along C2 you will integrate, and then if you total sum up, means you are arriving from 0, 0 to 1, 1, 1 along different path. So now, so these are to also, you can understand that C1 and C2 are non-overlapping curves. That also is important. Okay, they are, means you have not started between C1 means from here. It is no, these are non-overlapping curves. Okay, that also you should understand. So along C1 and along C2, you can integrate in the same fashion. You can find out the values and sum up. Okay, so let me to finish that, and then we will decide. Okay. So so you have the C1 is, I just write Ti plus Tj. Okay, 0 less than equals to T less than equals to 1, and C2 is Tk, 0 less than equals to T less than equals to 1. Okay, now integration C1 f of x comma y comma z ds. Okay, so I'm just writing here, this is a velocity vector magnitude. I think it is very easy to get differentiation of this, what, I plus j square root of 2. And for this case, velocity vector is square root of 1, that is 1. Okay, now along C1, z is 0, x is t, and y is t. Okay, so integration C1, or I should write it 0 to 1. Okay, x minus 3y square plus z, if you recall, time ds, so you have to evaluate at t. Okay, so that is ds, so that's going to be integration 0 to 1. You have x is t, y is t, z is 0, so t minus 3t square time ds is mod v of t time dt, so square root of 2 time dt. Okay, now this is equals to square root of 2. Now integration t square by 2 minus t cube, 0 to 1. So upper limit minus lower limit, again lower limit will not contribute anything. So upper limit will contribute 1 by 2 minus 1. So that is minus 1 by 2. So okay, so what you will get is equals to minus square root of 2 by 2. Now similarly, integration C2 f of x comma y comma z ds is equals to integration 0 to 1. You have x minus 3y square plus z time ds. So that is equals to 0 to 1. What is z is t and rest is 0, t time dt. Mod of v of t is 1 here. So now if you integrate, it's t square by 2, so that is going to be, now upper limit minus lower limit will lead to 1 by 2. Now, so therefore, now this implies integration over C1 f of x comma y comma z ds plus integration over C2 f of x comma y comma z ds is equals to minus square root of 2 by 2 plus square root of 2 by 2 plus 1 by 2, and which is not the same as what you have just observed. Okay. So just 1 by 2. So that's going to be 1 minus root 2 by 2. So this is certainly non-zero, not equals to integration cf of x comma y comma z ds. So what it also tells you that from a starting point to end point, if you choose a different path than line segment, that was a straight line from 0, 0 to 1, 1, 1, okay, it is getting completely different value. Okay, if you choose a different path, means you don't have you don't see any path independence here. Okay, and of course people will be happy if you have a path independenceness. Okay, with the problem. Okay, means then you will choose a way with which you can feel means like in this way you can go easily. So it is necessary to define path independence. Okay? And and also we have to impose some conditions. Okay, so that the integral is path independent. Okay, that we will see. Okay, maybe a little later. Now let's go back and check the example number 2. Okay, so now in the rest of the example, okay, second and third, I will try to give you the parameterization of the curve. Okay, rest means finding the integral is up to you. Okay, so in example 2, so he's saying that you have to evaluate integral c2 plus x square y ds, where c is the upper half of the unit circle in the xy plane. Okay, so 2 plus x square y. So you have example number 2. You want to evaluate this line integral, that is c2 plus x square y ds. And what is c? C is the upper half of the circle, upper half of the unit circle. Okay, this is minus 1 comma 0, 0. Oh, sorry, 1. And unless it is mentioned, we will say it's a anti-clockwise direction is a positively orientation. Okay, if it is so we will mention if there is any clockwise direction. If it is not mentioned, means you have to know the from positive means from on the positively orientation means anti-clockwise. Okay, so this C is the curve. So you can certainly find out what is the parameterization of this curve. C is you have cos of ti plus sine of tz, and you have 0 less than equals to t less than equals to pi. So I told you this t is a dummy variable. Instead of t, you can use theta as well, cos theta, sine theta, and 0 to pi. That also you can do. Okay. So now to evaluate this line integrals, we have all the things, all the information. So certainly you can identify that. So you have given with r of t is equals to cos of t I plus sine of tj. Now dr by dt is equals to, you can certainly differentiate sine t component wise. Okay, cos t of j. And you can certainly find now magnitude of this. That means velocity vector, which you require. That's the square root of sine square plus cos square, that is 1. So you have this line integral is equals to integration. So t limit is 0 to pi. 2 plus x square y. So x is cos t. So cos square t. Y is sine t. ds is mod v of t dt. So that is 1 time dt. Now you have to evaluate this. Okay, that this integral now is a real valued integral. Okay, and that you can solve. Okay, certainly. Why? Because the cos t derivative is sine t, it is sitting in the product. You can use that fact. So your example 2 is solved. Okay, you can find out, fix the final, you should find the value. Now let's look at the example number 3. So you have to evaluate the following, where C is the curve joining the line segment from so and so. First, you should look at this in the different manner. Yes. Okay. So means you see that how this and these are all are seen. Okay. So if you want to evaluate this, so I can rewrite this integration C time yi plus zj plus xk dot product with dxi dyj plus dzk, which is nothing but dr. Okay, so just going to repeat the things now. Let's look at this. So example number 3, you have to evaluate the following integration C by dx plus z dy plus x dz. Okay, so I can write this as integration C f dot dr. Okay, so you can multiply and divide by t later on. Okay, what is f here is yi plus zj plus xk, and certainly what is r? What was r? R of t is equals to x of ti plus y of tj plus z of tk. So from here, certainly you can analyze that what is dr, differential component, is nothing but dx comma dy comma dz. I'm writing in the vector notation. This part. Okay, in the direction of I dx, in the direction of j in dy, in the direction of k is dz. So if you perform f dot dr, you will get the same. You know how to perform the dot product. Now, okay, so there are means if you what is dr is I'm just if instead of t, if you use the arc length parameter. Okay, so I will try to now give you the some you can say means a real life example, or you can say okay how this will relate with the real phenomena. So now if you have this dr by ds, what it will be dr by ds? It's going to be at any point, it's going to be a tangential vector. Okay, because you are changing r with respect to the arc length, it's going to be. So if I'm going back and I just use the graph here. Okay, I will just use the graph here. So at any point, if you find the tangential vector, it's nothing but with respect, this is a t if I denote it by d. So the tangential vector can be obtained by this dr by ds at any point. It's valid. So, okay, so if you multiply by, so now from here, so I hope you got this from here, this implies d ds equals to dr. From here, because see, you know, with respect to first derivative, you can do this stuff. Okay, for the second derivative and so on, you can't do that. The two things are not in favor. Okay, for first derivative, first derivative, the things are in favor. Okay, and so again, I should mention here, EDS, what it would denote is the unit tangent vector along the curve. Okay, so F dot dr. Okay, so I hope if there is any doubt, you just let me know. So now let's get back to our that final one. So dr by ds is nothing but will be the tangential vector. Okay, unit tangent vector along the curve. Now then F dot ds. So if you say this F is representing a force throughout a region in space, so I have already mentioned, so if this F vector is a vector, okay, which is in means in 3 dimension, it may be f of x comma y comma z is can be generally m of x comma y comma z I plus n of x comma y comma z j plus p of, I'm just batching with a book notation, okay, x comma y comma z k m and p. Okay, so this F is represent a force, or it may represent a fluid flow, okay, or velocity field. Okay, so it means it may be a force of, again I mentioned already, gravitational force or electromagnetic force of some kind. Okay, so what this F dot EDS represent is nothing but this will represent the scalar component. So dot product, right? Scalar component of this force field, you can say, in the direction of the curves, so in the direction of this T. Okay, in the direction of this T, scalar component of F in the direction of the T. And now, so if F represents a force, and if you apply the force, okay, if you apply the force, this F is a force. If you apply the force and you move along the tangential vector, okay, and if you so unit tangent vector TDS, that will denote the work done in this small element dx. So if you integrate all the over the complete means or along the complete curve, it will give you the total work done. Okay, so or if it is if instead of force it represents the velocity field of a fluid flow for a reason in space, then it will give you the fluid flow along the curve. Okay, now there are now different phenomena. Suppose you are having the end point and terminal, end point and starting point are meeting. Okay, so you are moving along the curve means you are drawing a circulation around the curve. Okay, so that also known as, if the curve is closed loop, then you have the it will be that integral value, it will be called that circulation around the curve. Okay, so let's do this now. Let's finish this problem now. We are now, so I have already, so this is going to be smooth. Yeah, so now everything is in your hand now. So C is what is C? Let me here. Now what is C is the line joining, you have something 200, 345, something like that, right? 200, 345 and 340. 200, 345. So 200 to 345 to 340. Okay, so it's a line segment. So you have two line segments. So C1 equal partition is like C1 union C2. So C1 is the curve line joining 200 to 345. And C2 you can say there's a 345 to 340. Right? So not that here you are means like 20, so it's 2 means here denotes the direction from where to where you are moving. Okay, now you can find out the equation of the parametric equation, right? So for this C1 is we have this is R1 of t. What is x of t is going to be x minus 2 by 3, right? So it's going to be x equals to 2 plus 3t I plus 4t j plus 5t k, and t is 0 less than equals to t less than equals to 5. What about C2 is R2 of t is equals to. So you have x minus 3 by 3, x minus 4 by 4. Right, sorry, wait a minute. So this is, wait a minute, 3 minus 2 is 1, right? Yes, so 3 minus 2 is 1. So that is here is 2 plus t. Okay, right. So R2 is going to be so x minus 3, x equals to 3, y equals to 4, right? 3i plus 4j, okay? And z minus 5 by 0 minus 5. So 0 minus, so minus 5t, 5 minus 5t, right? Yes. Plus 5 minus 5t. Okay. Yes? Any doubt here? So, and t is running from, so 345 to 340. So t is is here. So x minus 3 by 3 minus 3, x minus 4, y minus 4 divided by 4 minus 4, z minus 5 divided by 0 minus 5. So z equals to 5 minus 5t, that's fine. And the t limit is what? Is going to be so you are means you have started with the 345 means t equals to
From 0 to
0
1.
to 2 equals to 1. Yes, t equals to 0 to 0 less than equals to t less than equals to 1.
Sir,
Right?
in first also it will be from 0 to 1.
It will be, yes, it will be 0 to 1. Yes, exact. Okay, so this is going to be 0 to 1. Yes. So because we have to be careful here, the limits as well. Now, once it is 2 to 3, yes, 4. Yeah. So when you have t equals to 0, 2, 4, 2, 0, 0. And when you have t equals to 1, you have 3, 4, 5. Yes. Fine. So now you are now everything is with you. Okay, so now along C1 and along C2, you have to evaluate this. So you have for C1 case, x equals to 2 plus t. You just write all the things. Y equals to 4t. Z equals to 5t. And solving for this C1, you can solve it for C2. T lies between 0 less than equals to t less than equals to 1. So from here, you can have dx is equals to. So there are multiple ways to solve this. Okay. Now dx equals to dt, dy equals to 4 times dt, and dz equals to 5 times dt. Right? So what is dr then? Dr is nothing but dxi plus dyj plus dzk. So it's going to be, I'm just replacing dx by dt, 4 dt and 5 dt. So you have, this is I plus 4j plus 5k times dt. And what is f is, what was f is yi plus zj plus xk. Okay, so yi plus zj plus xk. So this is equals to, what is y is 4t, what is z is 5t, plus x is 2 plus t. Okay. So, so yi, so 4ti plus 5t j plus xt case 2 plus t time k. Okay, how much time we have? Let's see. Okay. So now what you have to find out finally is f dot dr. So from above and here, so you can find out, this implies f dot dr is equals to, we are talking about along C1. So it is going to be 4t plus 5t time 4 plus 2 plus t time 5. So that is equals to 4t plus 20 and plus 5t. So 20 plus 5, 25 plus 4 is 29. 29t plus 10. Now, this is integration C1 f dot dr is equals to 0 to 1, 29t plus 10. Yes, of course, dt is missing. Okay, dt. Now you have, 29t square by 2 plus 10t, 0 to 1. So 29 by 2 plus 10. Okay, so that's going to be 49 by 2. So similarly, you can go for integration over C2 and then put the final sum. That will give you the complete line integral over the entire curve C. Okay, right. So we have solved all the 3 examples. Okay. Now we have seen already vector functions. Okay. So just now I have defined a vector function in 3 dimensions. that f of x comma y comma z has 3 dimensions I, j, k. So in each direction you have a function of 3 variables in general. Okay, so now we are going to look at the specific type of, so it will give you some type of feeling of a field where something is moving, okay, along some certain directions. Okay, so let's have this. Okay, so let's have this is let's have some examples, and then we will define the vector field, okay, on a domain. So you have here, so first vector field is this first figure. Okay, I just try to grab this from the book. Okay, and here it is denoting the streamlines in a contracting channel. So this is, here is a contracting channel, which you can understand this by a river flow, or okay, you can understand by the river flow, means somewhere it's getting contracting. Okay, and you can say this is a direction along which it is moving, means you have the rate that most rapidly moving, okay, in this direction. Okay, and you will certainly find that gradient and all that direction. You can also find out what is the most rapidly increase or decrease there. Okay, so it is very clear from here that towards this contracting channel, that water is speeding up. Okay, what it result in the velocity vector increase in the length. Okay, so certainly here the flow will be more, here will be coming in the less. Okay, right. Now let's look at the second figure. Now it's a wind tunnel. Okay, it's a wind tunnel. So velocity, it means here you have in the wind tunnel, means you have a wind is moving, and how you have analyzed these directions is by giving some smoke there. Okay, smoke in the sense of, means like kerosene smoke. Okay, then along which the kerosene smoke is moving, that will means visualize the directions. Okay, along which this velocity vectors are flowing. Okay, now next figure is you can see this is a center of mass. Okay, which is the source of field. Why? Because everything is moving in the direction of the center of mass. Okay, of course, that then a gravitational force or gravitational field will take place, and so on. Okay, right. Now similarly here, so you have a projectile motion. So you have this is a velocity vector. Means at any point you are finding the tangent, right? Velocity vector moving along the tangent at any point. Okay, so this is a velocity vector, and it's a gradient vector over the surface. So this is a surface level curve f of x comma y comma z equals to c, and these vectors are nothing but getting by the gradient, by performing the gradient, and we have already seen that will be the normal to the surface, that we have already seen, okay, by definition as well. Okay, so we have these examples, okay, where you can see some vector fields. Okay, so let's define the vector field here. So a vector field is a function defined on certainly on a domain D in the plane or a space. So D may be a subset of R2 or D may be a subset of R3. So that assigns a vector to each point in D. If D is a domain in space, a vector field on D may be written as this. Okay, so a vector field is nothing but is a vector function, you can say. Okay, is a vector field is nothing but a vector function. Okay, where each component in general, with each component is going to be a function. Okay, and though these x, y, z are coming from that domain T. Okay, so that will certainly define a field which will give you, which will known as vector field. This is general. And very popular one is gradient field, another is potential field, and so on, that we will know soon. Okay, and it is very simple to follow that gradient field. How will you obtain of a differentiable function? By just getting the gradients, just performing the gradient of the this differentiable function f, you will get the gradient. So for example, you have this, find the gradient field of this. It is very easy to find out the gradient field. So you have been given with f of x comma y comma z equals to x into y into z. So you know fx is yz, fy is xz, fz is xy. So grade f, vector field will be given by yzi plus xzj plus xy. So that will give you the gradient field. Okay, right. For the given function, given differentiable function f of x comma yz equals to x into y into z. Now another important field is conservative, where the principle of conservative applies. Okay, so a vector field is called conservative if you are able to find a differentiable function f such that this vector function, the vector field, can be represented as a gradient. Okay, so you have a vector field f, you will say it is a conservative if it can be represented as gradient of some differentiable function f. Means scalar function, means scalar function which is not a vector. Okay, so if a vector field can be represented in this form, then we say that that vector field is conservative. Otherwise, it is not conservative. Okay, right. And that f has some physical name attached with it that is known as potential. Okay, that will be giving you the potential of the vector field. Okay, so here is an example to find a potential of the vector field f. So by looking at this condition, you will be definitely able to find the potential if it exists. Okay, so I am right now just giving you the hint of how to find the potential of a vector field f. Okay, so this is an example by example. So f is given to be is 3 plus 2xy, 3 plus 2xy I plus x square minus 3y square z. Okay, what we are interested in, we are want to find f if exists. That's a very important. It will not exist for every vector field, such that f is equals to grade f. So grade f means fxi plus fyg in the two-dimensional, and you have the f definition, so solution. So if such things happens, then it must be true that fx must be equals to 3 plus 2xy and fy is equals to x square minus 3y square. Now, how will you proceed further? So you have fx equals to 3 plus 2xy. So now what I can do is integrate partially with respect to x. So when you integrate partially with respect to x both sides, then you have to treat y as a constant. Okay, so I'm writing integrating partially with respect to x. So what it will give you, f of x comma y is equals to 3x plus x square y. Keeping that mind, 3 integrate partially with respect to x means 3x. 2xy integrated partially with respect to x. So x square, 2x is x square. Y is a constant, you have to treat y as a constant. Okay, plus some additional constant. So that constant either is a fully constant or it may be a function of y. You can see partial derivative of f with respect to x will be same. Now, this now differentiating. So I have this, you can say 1 or you can say 3. Okay? Integrating 3. This is 4. This is 1. This is 2. So differentiating 4 partially with respect to y. What you will get is fy is equals to 3. Sorry, 3 will not be there because partially with respect to y, first term is 0, second term is x square plus h dash of y. Now, to become a part of this potential fy, 5 from 5 and 2, they both must be the same. Okay, so from 2 and 5, what you will get is x square plus h dash of y is must be equals to x square minus 3y square. Right? Yes. Now x square will get cancelled and h dash of y equals to minus 3y square. So this is h dash of y equals to minus 3y square. Now it's a function of single variable. You can easily integrate by following variable separable method. So h of y is equals to minus y cube plus some constants. Now it's a total derivative. So therefore f of x comma y is equals to 3x plus x square y plus h times h of y, that is going to be minus y cube plus c. So this will give you the potential. Now, when you will not get the potential is you will have here some type of situation where it cannot be solved. Or you can say some more information is required. Okay, right now that we can comment. Later on we will see how we will verify the first stage itself whether it's going the potential field exists or not. Okay, right. So the further we will do line integral. We have so this already has been defined actually. Okay, that we will see in the next class. Okay? And if you have any question, you can ask.
So,
Yes.
so is it possible for you to read the chat? There is a question like related to exam.
Set wise relative marking. What is meaning?
So like particular students with same set, so it would be marked accordingly.
See, I have put up randomized questions. Okay, so in some cases, somebody has I mean, it is very, I can say it is a very less chance to get all of the questions are hard. Okay, so somewhere it's like finding the maxima, minima you may get, or somewhere you will get absolute maxima, absolute minima, Lagrange multiplier problem. Okay, some double integral or volume integral. So these all are, I think I have tried to take care of everything there itself. Is somewhere you will get the easier problem, somewhere you will get the This means you can save your time. So it is I don't think so. It is necessary. Okay, we will see if means if someone is yes, if somebody is coming up like because of the lack of time, means because every problem has means length. Okay, lengthwise means if you are supported with your rough notes that you have submitted, then we will see, we will look into it. Okay, it is a very special case.
Okay, sir.
Okay, then thank you.
Thank you, sir.
Thank you, sir.
Okay, sir.
Thank you, sir.
Thank you, sir.